So in this chapter, we'll learn about undirected graphs and two main ways to traverse them. Let's start with the basics. What is a graph? A graph is essentially a network made of vertices or nodes and edges that connect them. You can think of it like a structure that models relationships between objects. The formal notation for a graph is G equals VE, where V represents the set of vertices and E represents the set of edges. When we analyze algorithms involving graphs, we often use N to represent the number of vertices and M, or sometimes E, for the number of edges. This notation becomes especially useful when discussing time and space complexity. Now, there are two classic ways to traverse a graph. Breadth first search, or BFS, which explores all neighbors level by level, moving outward from a starting node like wave spreading in the water. And depth first search, or DFS, which dives as deep as possible along one branch before backtracking, kind of like exploring one long tunnel before coming back and trying another. Both approaches are fundamental for understanding graph algorithms. And to make this more concrete, imagine a road networking city. Every intersection is a vertex, and every road connecting two intersections is an edge. If you were using BFS, it would be like exploring all nearby streets before moving farther away. If you are using DFS, it's like following one long route until you can't go further, then turning back. And graphs are everywhere, not just in computer science, but in social networks, transportation systems, biology, recommendation engines, and data science applications like clustering or link prediction. In social networks, for example, people are nodes and friendships are edges. In biology, graphs can represent protein interactions or neural networks. Understanding graphs and traversal methods isn't just theoretical, it's highly practical. Many lead code or interview questions rely on BFS and DFS, and beyond that, they form the foundation for more advanced algorithms like shortest path search, connected components, or even web crawling. So overall, mastering these two traversal techniques help us reason about how data is connected and how information flows in complex systems. If we wanted to find the shortest route in the subway system, which traversal should we use? BFS or DFS? Why? We should use BFS here. This is because it explores our neighboring nodes level by level, meaning it's finding the shortest path in terms of the number of edges from a starting station to a destination. In a subway system, every stop is a node and every connection between stations is an edge. So BFS guarantees that first time you reach a station, you've taken the minimum number of transfers possible. DFS, on the other hand, going deep along one route before backtracking. It might find a path, but not necessarily the shortest one. And before I finish, I'd love to hear about your thoughts. Which traversal do you think would be more efficient in real-world systems like recommendation networks or web searches? Thank you.